This video will illustrate the methodology required to solve a question that requires trigonometric substitution that ends up using the secant substitution in the example. Let's say we have to solve the following integral. Integral of dx over x squared times square root of x squared minus 9. The first step in the integration problem-solving technique is to determine whether this is a series of simple powers of variable x. Because we have a binomial in the denominator inside the square root, we are not going to be able to multiply this out to yield a series of powers of x in the numerator without using some kind of an approximation. So it's not going to be just a regular power rule. Step 2 is you look for a function differential relationship. We have a relationship inside the square root of x squared minus 9. The differential of that statement would be 2x dx, not 1 over x squared dx. So the differential of this statement, x squared minus 9, is not present. So we go to step number 3. And is this a standard form? And the answer is, of course, this is not a standard form. There is no integral on our formula sheet that has this as its solution. Step 4, you look for trigonometric identities. In this problem, there are no trigonometric functions. So you're not going to use trigonometric identities as your methodology. You just skip that step. Step 5, could this possibly lead to the arcsine or arctan form? The arcsine form does have a square root on the bottom, but it has the number first minus the function second in the difference of squares. And in this problem, we clearly have the function is first and the number is second. So this cannot possibly lead to the inverse sine form. It cannot lead to the inverse tan form because the inverse tan form does not have a square root in the denominator and it does not have. So we go to step 6. We identify here that we see a difference of squares in this problem. And so we see a difference of squares, but it doesn't follow any other methodology discussed previously. So because we see the difference of squares, we're going to try step 6, trigonometric substitution. And to review, when you see the difference of squares where the number is first, a squared minus u squared, your constant value is first, then the function second. That's the u equal a sine theta substitution. The difference of squares where you have the function first, u squared minus a squared, that's the secant, u equals a secant theta substitution. And a squared plus u squared, the sum of squares, is the u equal a tangent theta substitution. So we need to compare which of these forms are present in the question that we have. And it is clear that we have the function first difference of squares. So u squared minus a squared. So we're going to end up using this substitution, let u equal a secant theta. So u squared minus a squared is identified in the problem, and if we original problem, the u squared is x squared in our problem, so that means that u has to be x. And the a squared is a 9, so that means that the square root of that is 3, so a equals 3 in our particular integral. So we're going to use let u equal a secant theta with u equal x and a equal 3 means x is going to be replaced in our problem with 3 secant theta. So if we replace x with 3 secant theta, that will get rid of the x here and here, but it does not get rid of the differential in the numerator dx. So we need to have the differential of this substitution. If x is 3 secant theta, the differential of that statement is 3 secant theta tan theta d theta. So that's what's going to be substituted into this integral. So again, here's the original problem, and we had the two substitutions, x equals 3 secant theta and dx equals 3 secant theta tan theta d theta. If we substitute everywhere we see x, we're going to replace it with 3 secant theta, and everywhere we see dx, we'll replace it with 3 secant theta tan theta d theta. So if we do that substitution, the dx in the numerator becomes the 3 secant theta tan theta d theta. The x squared, when you square x, you have 9 secant squared theta. And when we take that same x squared and plug it into the function, inside that square root, we get 9 secant squared theta for that as well. Notice you can always check when you do trigonometric substitution. That the coefficients inside your difference of squares match up. Those two numbers have to be the same. Every time you do trigonometric substitution, the two coefficients in your difference or sum of squares will always match up such that it can be factored out. So if we actually factor out the 9, which is in the denominator, and the root 9, which is inside of the difference of squares, factor both of those constants out, and because they're constant, they come outside the integral. We end up with this 9 root 9 in the denominator factored out front. That leaves us with tan theta in the numerator. Secant theta, one of those is going to cancel. So we end up with a single secant theta in the denominator. And then inside the square root, we factored out the root 9. So all we're left with is secant squared theta minus 1. So the square root can be simplified and the constants out front can be simplified. So the square root, secant squared minus 1, that's an identity. Every time you do trigonometric substitution, you're going to end up with, in these cases, a Pythagoras Theorem identity. So if we replace secant squared minus 1 with a single term, and that's the whole purpose of trig substitution, is it's going to reduce the two-term statement into a single term. So inside the square root, secant squared theta minus 1 is tan squared, and the factor out front, 3 divided by 9 is 1/3, and root 9 is also 3, so we get 1 over 3 times 3, which reduces to 1 over 9 out front. Notice now that inside the integral, we have tan squared theta inside of a square root. Well, that reduces to just tan theta. So the tan theta factors are going to cancel. Those will divide to 1. And we are left with 1/9 integral d theta over secant theta. But of course, the reciprocal of secant is just cosine. So 1/9 integral d theta over secant theta, 1 over secant theta is cosine. So we have 1/9 integral cos theta, and that is the end of the substitution part of trigonometric substitution. The output is a new trigonometric integral. And whatever you get at this stage, it might be a integral that involves trigonometric functions where you're going to do a simple substitution. It might require a standard form integration. It might require identity substitution. You use whatever method at your disposal to solve the trig integral. So if we start over at the beginning, this is not a power of theta. It's not a function differential. The only function here is cosine. Differential of cosine is negative sine theta d theta. That's not here. So it's not a function differential relationship. So if we go to step 3, is this a standard form? The answer is yes. You should recognize this as a standard form which is on your formula sheet. And so the solution to integral cosine is positive sine theta plus c. So if we substitute that solution right from the formula sheet in for cosine theta d theta, we end up with 1/9 sine theta plus some unknown constant. So that's the answer. We've now solved the integral. There's no more integral anymore. We've got a solution. The problem with this is that even though this solution is correct, it is not the right variable. It's not the variable we started out with. Our original problem has variable x in it. So our solution should have variable x in it too. And it currently doesn't. So we have to undo the trigonometric substitution. And the way that we undo the trigonometric substitution is by drawing a right triangle that corresponds to the original substitution, and then finding whatever trigonometric relation we need from that triangle. So again, we had our answer. The integral is 1/9 sine theta plus c. So if we return to the original substitution, remember that it was x equal 3 secant theta. That defines the trigonometric ratios for a right triangle. If we rearrange this equation, we get that the substitution for secant of angle theta would be x over 3. And since secant is the reciprocal of cosine, or cosine is the reciprocal of secant, cosine of the angle theta must therefore be 3 over x. So if we draw a triangle, a right triangle, and place our angle that's relevant here, theta, at a position in this right triangle, so we've got to have a 90-degree angle there. If cosine theta is 3 over x, cosine theta is the ratio of sides adjacent over hypotenuse. That means the adjacent side to angle theta, which is going to be located here, that's going to have to be 3. And the hypotenuse, which is located here, is going to have to be variable x. We now have a missing side in this right triangle. You can solve that with, as always, Pythagoras Theorem. A squared plus b squared equals c squared, where c is the hypotenuse of the right angle triangle. In order to find the missing side, then, we just take the square of the hypotenuse, which is x squared, and minus the square of the adjacent side, which would be 3 squared, or 9. So we end up with square root of x squared minus 9. And an excellent way to check that we are on the right track is if we produce the missing side in our right triangle, notice that we end up with a difference of squares, which is exactly the same as the difference of squares that we started with in the original question. So that's a good here. So our solution is related to sine of theta. So we need to read sine theta from this triangle and then substitute that into the answer. Well, sine theta is just the ratio of opposite over hypotenuse. So it's going to be the ratio of the opposite side divided by the hypotenuse side. So sine theta would be square root of x squared minus 9 divided by x. And we're going to substitute it into our solution. So 1/9 sine theta plus c would become 1/9 square root of x squared minus 9 over x plus c. And we can join the 9 and the x in the denominator together, and we don't need the 1 out front. And so that can be rewritten as square root x squared minus 9 over 9x plus c. And this is the solution for this integral. You can check the answer by doing a derivative. You can do the derivative of this statement, and you can check that we actually get dx over x squared root x squared plus 9 as the answer.